Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So this is the, I'm again starting with the last slide from the last lecture, and we figured out what was the average depth of the block, and that came out to be, the average depth was 3 blocks here. Where does that average occur? It was at block number 5, this average, and we found out the resultant, and the resultant came on this. Okay, so now we proceed with one of the real life examples of moment. So the question is, an elliptical gate covers the end of a pipe 4 meters in diameter. So this is the elliptical gate. I will delete this, but I am trying to show where those different objects are. If the gate is hinged at the top here, okay, what normal force F applied at the bottom of the gate is required to open the gate when the water is 8 meter deep above the top of the pipe? Okay, so this, and the pipe is open to atmosphere. Okay, on the other side here, neglect the weight of the gate. Okay, so here we have seen, this is how this elliptical gate looks. This is the cross section. Okay, so once you have understood the question, we can proceed with the solutions now. Okay, so I have kept this figure on the right side so that you are able to follow what we are going to do. So what is the pressure datum? This is atmosphere. Okay, so the resultant force is going to be the pressure at the centroid into area, that we have seen in the derivation done last lecture. What is the area? Area of the ellipse that we have seen is pi into AB. Okay, what is the HC? So just taking you, for HC, first we need to understand this is the y axis that we have assumed. Okay, and this is the theta that we have assumed. Okay, so HC is 10 meter actually. Why? 8 meter plus 2 because of the ellipse. Depth to the centroid. Very clear? So FR is going to be rho g HC pi AB. So rho is 1000 kilogram per meter cube, g is 9.8, height of the centroid that we have seen is 10 meter, because 8 meter is this water depth and the depth location of the centroid is further 2 meters below this location. So 10 meters, pi is pi, A is 2.5 and B is 2, as we have seen the values of A and B from the previous slide here. A is 2.5, B is 2. Okay, so I am just going back. So here, so FR finally comes out to be 1.54 meganewton. Very simple to calculate. Okay, meganewton is 10 to the power 6 actually. So fine, so we proceed to the other part now. So what is the location of the resultant? So we need to find out YR and XR. YR is given by YC, correct? So IXC by A from the set of the areas that we had seen shown in the last lecture is given as A square by 4. If you are confused, you can go and see it in the last lecture notes. YC can be written as HC by sine theta. This we have already seen in the derivation. Okay, where sine theta is 4 by 5 for n, because minor axis and major axis is 2.5 and 2. So YR can be written as YC plus A square by 4HC sin theta, right. If you just put the value of IXC and A, you will get this result, this value. So YR is YC plus A square. If you substitute the value of sin theta as 4 by 5, you will get YC plus A square by 5HC, and this comes out to be 0.125 meter. As ellipse we discussed this, it's symmetric about the centroid, so we won't have any XR, and XR is going to be 0. So very simple calculations here, correct. Now the most important part is force that is required to open the gate. So what all do we know? See, YR is 0.125, right. So this will become 2.5 plus 0.125, that will be 2.625, correct, and this is 2.5 meter, this is 2, and this is total length, L total. So how do we find the required force here? So we have to take moments about the hinge. Hinge was here, so moment about hinge will be 0, and this means force into length of total will be the resultant force into length of, we already know length of the center of pressure, and the resultant force we already know. We need to find out this F, we already know L total. So F total will be FR LCP by L total, and on substituting the value 1.54 into 10 to the power 6 for FR, LCP is 2.625 as can be seen here, and L total is very simple, it's 5 meters, right. So yeah, so this value will come out to be 809 kilonewton. Okay, so this makes sense, correct. So this makes our problem complete. What I am going to do again, I will erase all the ink on this slide, and now we can just proceed to the other part. So we also need to know to wind up the the forces on the plane surfaces. Some of the important results: the average magnitude of the pressure force is the pressure at the centroid. This is what we have seen, correct. The horizontal location of the pressure force was at XC. Why? In this particular problem, the gate was symmetrical about at least one of the centroid axis. In that case, it was 0 XC. The vertical location of the pressure force is below the centroid. This we have answered so many times, that because the pressure increases with depth, correct. Okay, so now this is so now we need to calculate the pressure on the curved surface. So this surface here, you see this, okay. So how? We need to know the horizontal component, we need to find out the vertical component because it's curved, right. So this is one of the examples. My question to you is, what is the magnitude of the vertical component of force on the cup? Tell me. Force is pressure into area, correct. Pressure is rho GH. Putting it rho GH, right, area is pi r square, and this actually is the weight of the liquid supporting it. So that will be the force, vertical force, okay. So to sum, the vertical component of the pressure force on a curved surface is equal to the weight of the liquid vertically above the curved surface and extending up to the surface where the pressure is equal to the reference pressure. This is the thumb rule. So the vertical component of the pressure force on a curved surface is equal to the weight of the liquid vertically above the curved surface, okay, and extending up to the surface where pressure is equal to the reference surface. So that means up to the free surface in our case. Okay, so we will understand this particular part using a solved example. This is pretty simple to understand. So Yeah. So this is a gate. All the components are indicated. W1, the lengths are indicated 2 meters. W1, W2, 2 meters, 3 meters. Water. This is water. Okay. So let me erase this. We have to find the resultant force, both the magnitude and location, on a 1 meter wide section of the circular arc. So actually this is 1 meter wide in that direction, in the other direction, not shown here. So what is going to be the vertical force? It's going to be what we, according to the definition, it should be the sum of the liquid above this curved surface extending from here up to the free surface. So basically what is that? W1 plus W2. W1 is very simple, it's 3 meters into 2 meters into 1 meter, because that is the dimension that is told, 1 meter wide section, into gamma of water. This one, it's pi by 4 r square. So pi r square is the total area, but it is 1/4. So pi by 4 r square into 1 meter into gamma. Very simple calculation. This comes to be 58.9 kilonewton plus 30.8 kilonewton, and in total it comes to about 89.7 kilonewton. Okay, very simple. Now we also need to know what the horizontal component is. So horizontal component is the pressure at the centroid multiplied by area. But what area that is? So area is 2 into 1. So pressure at the centroid is, this is centroid, right, 1 meter below. So 3 plus 1 4, gamma h is the pressure, and this is the area, 2 meter into 1 meter in that. Okay. So this, the horizontal force is going to be 78.5 kilonewton. The vertical component line of action goes through the centroid of the volume of water above the surface. Okay, and that is very understood, you know. So this is A. Now we have to take moments about the vertical axis through A here. Okay. So if we want to find out the line of action, that is XC, XC we know already, right? Sorry, XC into FE will be equal to, the weight is acting, okay, 1 meter from there, W1. However, W2, I told, if you remember, I told you to remember this equation 4r by 3 pi in the lecture, that we are going to use this, and actually we are using this. This is 4 into 2 meter by 4 into 2 by 3 pi, and this. So okay, so let me erase this. Yeah, okay, so this is the 4r by 3 pi, and this will give us the location XC. So it will be 1 meter, weight was 50, W1 was 58.9, this we already know, W2 was 30.8, and the total vertical force we found out was 89.7 in the previous slide. So this is actually going to give us 0.948 meter, and it is measured from A with magnitude of 89.7 kilonewton. So this is the magnitude and this is the location. Okay. The location of the line of action of the horizontal component is given by YR is equal to YC plus IXC by YC into A. This is what we have seen before. Here HC is equal to YC. Okay. The depth height of the centroid is the actually also the Y, because we have assumed an axis in the vertical direction. So YR is going to be YC plus, if you look at this, so IXC by A will come out to be, you know, because of A square by 12. Okay, if you assume B and A as this, IXC by A is going to be A square by 12. Okay, as I have already indicated before, now they have also the this one here. So HC is going to be, in this case, what HC is, so 3 meter plus 1 meter, so that is 4 meter. So YR is YC plus 0.083 using this calculation. Okay, because so now to sum up, this is the horizontal force 78.5, this is 89.7 the vertical force, and 119.2 is the resultant force, and yeah, the distances are shown, 0.948 meter that we have calculated, 4.083 meter also we had calculated. So this solves our this problem of forces on curved surface. Okay. So this will give an overall picture of what is happening in this forces on curved surface. So the trick is that you use always the force balance and the moment balance wherever the curved surface is. As I told, the vertical force is the weight of the liquid above the curved surface until the where the atmospheric pressure is, or until the free surface, and the pressure, the horizontal force will be the pressure at the centroid into the area, projected area in the in, because surface is 3 dimensional, but in the plane of 2D, the projected area, that is very simple to do that. And so yeah, so we will be proceeding now to the last topic, that is buoyant force, after which we will also solve some problems. Okay. So I would ask you, the resultant force exerted on a body by a static fluid, this is quite important term here, in which it is fully or partially submerged, is going to be the projection of the body on a vertical plane is always, you have to fill this, is going to be 0. Okay. This means the two surfaces cancel, the net horizontal force is 0. Okay, that is very important. The vertical components of pressure on the top and bottom surfaces are different, however. So in the horizontal plane the forces cancel, two surfaces cancel, therefore there is no horizontal force, but in the vertical components of pressure on the top and bottom surfaces are different. The reason is very true, because at the top the pressure will be different and the bottom the pressure will be different, right? So this is, if you try to do an experiment, you place a thin water balloon filled with water in a tank of water, right, something like this. So this is the balloon, okay, and the this is filled with water, and this is also filled, this is placed in a tank of water, okay. So the buoyancy force we call it rho GV. I am asking what is the net force on the balloon, should be 0, right? It's in, if it is an equilibrium, net force should be 0. Here, does the shape of the balloon matters? No, because if you do that experiment, it doesn't really matter, okay. Now the question is, what is the buoyant force on the balloon? Actually I have not derived it, but since you have already done it in your fluid mechanics class, the buoyant force on the balloon is actually the weight of the water displaced. So this is the most important thing to note, that the weight of water that an object displaces is buoyant. I'll just use the eraser. It's called the buoyant force. This is very important. Okay. So proceeding forward with these two, this particular concept, what is buoyant force, we are going to actually solve a problem. So it says a block of wood of density rho 1 is floating completely submerged. I think the spelling here is wrong, but yeah, I'll delete T, at the interface of two liquid rho 1 and rho 2, rho 2 and rho 3, yeah, right. So it should be rho 2 and this should be rho 3. I am very sorry for this typing error. If V2 is the volume of the block in the upper liquid, okay, and V1 is the total volume of the block, we have to show this equation. First of all, when you have any questions like this, the first and the most important step here to do is draw the figure. Okay, so I am not very good at this, but anyways we'll try. So let's place the block here first. Okay, this is block. Okay, let's put a liquid layer here and another liquid layer here. Okay, so block, this density is rho 1, for example, this is liquid 3 because we are assuming density as rho 3, and this is liquid 2, and that is why this is rho 2. Okay, so I think this is the correct representation, and now we also have to say this is air, right? So this is the this is the complete diagram. Now I think the question would be more clear to you. So as always I am going to use I am going to use white screen. So we say let V2 is equal to volume of the block in the upper liquid, that is liquid 2, right? So V1 will be equal to V2 plus V3, correct? Since the block is in equilibrium, consider the weight of components of the block and hence the two displaced liquids to obtain. So how do we get that? Rho 1 V1 G is equal to rho 2 V2 G plus rho 3 V3G, right? Thus rho 1 V1 is equal to rho 2 V2 plus rho 3 V3. That is correct. Or we can simply write V2 is equal to, using this equation here, rho 1 V1 minus rho 3 V3 divided by rho 2. Okay. Okay. Or V3 by V1 on the other hand can be written as V3 divided by V2 plus V3. Okay, from here, and this can V3, now V2 plus V3, V2 we can use from here, right? And this equation has actually come all the way from here, so it will be V3 plus, and V2 we are going to use, so it will be rho 1 V1 minus rho 3 V3 divided by rho 2 plus V3. Okay, fine. So we will be expanding this in the next white screen. So I am going screen on white. White screen. Okay, so V3 by V1 is going to be rho 2 V3. We are just simply expanding this, rho 1 V1 minus rho 3 minus rho 2 divided by rho 2. Okay, or 1 by rho 2 V1 by V3 minus P rho 3 so rho 3 minus rho 2 divided by rho 2. Okay, or this will, we take the denominator upside. Okay, so it will be rho 1 by rho 2 minus rho 3 minus rho 2 divided by rho 2 into V3 by V1 is equal to 1, or you simplify, then V3 by V1 come out to be rho 1 by rho 2 minus 1, or divided by rho 3 minus rho 2 minus 1, or rho 1 minus rho 2 divided by rho 3 minus rho 2. And this was what was asked in the derivation. So we have solved this problem. It's just nothing, just simply force balance in the vertical direction and some manipulation. I think you should practice that more carefully in your home. So now we are going to do the last okay problem. The problem says the body weighs 20 Newton and 10 Newton but weighed under submerged conditions in the liquid of relative density 0.8 and 1.2 respectively. Determine its volume and weight in the air. So yeah, what I am going to do, again a screen. It's very simple problem, but I think it will give you a thorough brush up. Let I have not selected the pen. Now I will select the screen, white screen. So let weight in air, B W, and volume is equal to V. Weight in liquid of relative density is equal to S, B Ws is equal to W minus gamma S V. Okay. So Ws1 is going to be W minus gamma S1 into V. Ws2 is going to be W minus gamma S2 into V, right? So what we do is we simply subtract first from the second, so it will be Ws2 minus Ws1 is equal to gamma V S2 minus S1, simply this minus this, okay, and therefore we can get V is equal to Ws2 minus Ws1 divided by gamma S2 minus S1, and we can simply substitute the values. 20 minus 10 in our case, gamma we already know 9790 into S2 minus 1 is 1.2 minus 0.8, and this comes out to be 2.55 into 10 to the power minus 3 meter cube, or the volume in liters can be written as 2.55 liters, and Ws can be written as Ws1 into gamma into S1 into V. So I'll take this calculation here. So Ws can be written as 20 plus 9790 into 0.8 into 2.5536 into 10 to the power minus C. Actually we are using this equation here, so it should be Ws is equal to Ws weight in air Ws, so it will be W, yeah, so 20 will add actually, and this will come out to be 40 Newton, right? So yeah, that Ws1 we have already found out because it was 20, so we are using this equation, so this is not very true, okay, so to calculate weight we are using this equation actually, fine. So this solves our question number last, okay. So with this we conclude the week 1, where we have studied the basics of fluid mechanics 1 this week. Next week we will be exploring fluid kinematics, fluid dynamics and the Bernoulli's equation, and we will conclude the basics of fluid mechanics 1 that would be required for studying the other important chapters of hydraulic engineering. So this is all for this week. Thank you so much. See you next week. Bye bye.